Well, AP Calculus BC, I am so proud of you guys. You made it through the dreaded infinite series units from last semester. It is all downhill from here. We actually only have 2 units left. This first unit focuses on 3 little subtopics: parametric equations, vector equations, and polar equations. And I'm going to try to say equations instead of functions because many of the equations that we analyze won't be functions. They won't pass that vertical line test. However, I will probably slip up almost 100% of the time and call them functions instead, but you get the idea. And then we just have one more unit left after this one, which is going to focus on differential equations, which we did a lot in AB, and just add a couple topics in. So definitely that downhill slope. Make sure you're keeping up with your free response practice so that you can keep your AB topics fresh in your mind, because 2/3 of that exam is still AB calculus. Only 1/3 is going to be this BC stuff. Without further ado, though, let's get to it. Most of these 3 little subtopics, parametrics, vectors, and polar, are going to start with non-calculus portions because it's been quite some time since we did these, and in fact, depending on which pre-calculus class you went through, you might not have even seen some or all of these, which is okay. A lot of these have really good ties, especially parametrics and vectors, to physics, and if you're in physics, you'll probably enjoy the connections. And I really feel bad because we don't have enough time to really delve deeply into any of them to the extent that we should, but I will do my best. Of course, there are many, many, many other resources out there if you want to go further in depth into any of these little subtopics. You'll also notice that I have borrowed but cited, because that's always the nice thing to do, many of these activities and problems from Nancy Stevenson of Clements High School in Sugar Land, Texas. She is a wonderful veteran teacher, been doing this a long, long time, and she shares a ton of resources, and so I've adapted a lot of them for this unit. Always important to cite your sources if you use them from somebody else from somewhere else. So let's get to it. What are parametric equations? Well, what this is going to do is, instead of giving us a single equation where it's an input of x and an output of y, and create some sort of curve, whether that curve is a line or a parabola or a circle or anything like that, the parametric equations allow us to split that single equation into multiple, usually more simple equations, oftentimes known as components. And you might think that's a little bit weird. You're like, why would I want to take one equation that does the job and split it into smaller ones, into extra equations? Sometimes they're not even smaller, sometimes they're more complicated. Well, I have a couple of reasons. First, once you get out of this 2-dimensional graphing and you add in a z-axis, or you go 4-dimensional or n-dimensional, it's much, much, much easier to create equations in parametric form. You usually do one equation for each dimension, as opposed to one single equation that incorporates all those variables, especially with writing a line. Once you get to Calc 3, hopefully you do get there, you'll find that writing a line parametrically is much easier than writing a line in a single equation. Also, and I mentioned physics earlier, physics has a really analytical view of motion, where instead of looking at the x and the y all put together, you usually split how a particle moves into its x movement, its x component, its side-to-side movement, and also how the particle is moving up and down. And then when you look at how far the particle moved one way, how far the particle moved another way, then if it started at the origin and now it's over here, then you get a nice understanding of what actually brought it there. Oh, it moved more to the side than it did straight up. So, how does this work? Well, parametric equations, at least in 2 dimensions, have the form: the x movement is some function of t, and then the y movement is some generally other function of t. So what we do is we use the purple equation to find the x coordinate, the yellow equation to find the y coordinate, and then we're done. However, both of those components depend on a third variable known as a parameter, hence parametric parameter. And typically that parameter is t. We take it to mean t is time. It's kind of weird though, because when you graph this on an xy axis, there is going to be no t, but t is the input anyways. You input something and then we have 2 separate outputs that we're graphing simultaneously. So let's see a quick example. Many times parametric equations are going to be written in parentheses like this, where you have one equation, comma, a second equation. Very, very common way. And actually, when we get to Desmos, Desmos requires you to input parametric equations that way. But for our first example, we'll see them separately. So given the parametric equations x equals 2t and y equals t plus 2, find the coordinates of the curve at, and we have two different t parametric, or we can call, or parameter or time values. So we'll start with t equals 0. Okay, fairly straightforward. We're just going to take this 0 and substitute it in for both of our values of t. So that, of course, is going to give us x equals 2 times 0, which is 0, and y is going to equal 0 plus 2, which equals 2. And putting that all together, then, we get that at a parameter, or I'm just going to use time easier, at a time of 0, the x-coordinate is 0, while the y-coordinate is 2. So when we plug in 0 to our parametric equations, we get that the particle is at the point 0, 2. Right, moving a little faster, we probably don't even need to show work here. When we substitute in 100, 2 times 100 is, of course, 200. And then we also end up with 100 plus 2, which is 102. Okay. Last but not least, these parametric curves usually start with t equals 0, a time of 0, and move in the direction, or I guess the curve progresses in a single direction. So if you were to draw a parabola from left to right, it's very typically shown with arrows like so, so you can see which way the curve is moving as time increases. If you were to draw the parabola backwards based on your time values, you would reverse the direction of the arrows to show which way the curve is going. Now, parametric equations can be a little bit tricky because you might look at these two and go, oh, those are both linear, so therefore, when we graph all of these points and connect them, it will make a linear function, and you could possibly be right. However, it gets a little bit trickier when you have a linear function and a nonlinear function. When you graph all of the points on there, what will that look like? So let's go ahead and try graphing that first. And to graph it, whenever we introduce a new graph, always important to go back and create a table that gives us good insight on the patterns and how everything's working together. I am again going to continue through and do the x component in purple and the y component in yellow, and I think we're just going to do all the x's at first. So when we plug in 0, we get 0, 2 is 4, 8, 12, and 16. X's are going up by 4 every time. Nothing bad. Now for the y's. 0 gives us negative 4, 2, 4, half of 4 is 2, 2 minus 4 is negative 2, substituting in 4, 16, half of 16 is 8, 8 minus 4 is 4, 36, half of 36 is 18, 18 minus 4 is 14, and then we substitute in 8, 64, half of 64 is 32, 32 minus 4 is 28. All right, well, what does this look like? Well, there's a bit of an issue here in that I think our graph probably doesn't cover all the different points that we need, but we can graph some of them. We have, of course, our first point, 0, negative 4. And then my next point is 1, 2, 3, 4, negative 2. And then 8, so let's see, it's 1, 2, 3, 4, 5, 6, 7, 8, comma, 1, 2, 3, 4. Looks to me like it's kind of increasing, maybe like a parabola, something like that. Right? Now, we have a couple ways that we can check this. The first way we can check is by using your calculator or Desmos. And I'll show you Desmos first and then your calculator second. I'd encourage you to try and use your calculator for the majority, but some of you may not have a calculator available, or you just like using Desmos, which I do often, and so I wanted to show you that first. So how do we use Desmos to graph this? Well, we are going to write this in this parenthesis notation that we saw up above. So I'm just going to pull up Desmos. We have this, we need parentheses, and I think it was 2t, comma, 1/2 t squared, then minus 4, wasn't it? Great. And then you look at this and you go, well, whoa, it just stops right there. our graph didn't stop right there, did it? No, our graph went this way, and in fact, I should probably have drawn a second set of arrows here to show which way it's moving, though the arrow at the end I think is pretty indicative of that. So why does it stop? Well, it stopped because Desmos didn't know what range of t values you wanted to plug in. So Desmos plugged in 0, that's how they got -4, and plugged in every value in between 0 and 1 to get this nice continuous curve down here, though I actually can't even click on it because Desmos struggles a bit with this. It just plugged in independent values. It doesn't see this as a full equation, and it stopped plugging in 1. Well, what if we went a little bit further? What if instead I wanted to go to 2? Oh, there we go. And 3, 4. That's looking pretty good. Can we make this go further? Let's make it do some work. Let's do 10. Ha! Looking like a parabola now, isn't it? We could go further, our 100. And we say, well, I think it looks like parabola, but what if it's actually a cubic? What if you're doing t times t squared, so it's t cubed, and we can't see the bottom half of the curve down here? Well, one thing you could say is, well, could we make t negative values? You can. It's not traditionally done, but it works just fine. So you could do it from -4 or -100. Maybe now you're pretty darn convinced it's a parabola. But what if it's a quartic? What if it's to the 4th power? Because that would look like a parabola. Or to the 6th power. How do we know for sure? So seeing the shape of the graph is nice. However, we're going to go a little bit further, and we're actually going to find the equation in y equals f of x form for this. And the way we do that is through a process known as eliminating the parameter. The parameter is the variable t. We want to eliminate it. How do we do that? Well, let's start with our two equations. We know that, keeping my colors, x is equal to 2t, and y is equal to 1/2 t squared minus 4. To eliminate the parameter, all we have to do is find some way to combine the two equations. I think probably the easiest way is to isolate t here and then substitute that into the other equation. So to isolate t, we multiply both sides by 1/2, and then we substitute. Y equals 1/2, and instead of t, we now have 1/2 x. Can we simplify that a little bit further? I think so. We have y equals, let's do the square first, right? We can distribute with multiplication. So that gives me 1/4 x squared minus 4, or putting this all together, 1/8 x squared minus 4. And there we go. Am I sure that that's right? Well, honestly, no, I'm not sure. So let's go back to Desmos and let's graph that equation and see if we got the right answer, right? We're now in that form of y equals f of x, which Desmos graphs very well. So we're just going to go here and we're going to say, okay, I think this is y equals 1/8 x squared minus 4. Oh, look at that. I think it matches up perfectly, right? I can take this off, put it back. That is the one. And so that's a really nice way to make sure that you've done everything correctly. This is all we're going to focus on today. I have 3 more examples that I'm going to go through with you. I think completing the table and making the graph are not too bad. However, I am going to walk through eliminating the parameter and checking these on different calculators. So if you're feeling pretty comfortable, you're definitely welcome to go through and fill these out. Especially there are going to be times like I'm not going to fill out this table, I'm not going to make the graph. I would like you to do that. But you might want to skip to the example that has your calculator involved, just so you know how you can do this on your calculator. So on problem 2, I'm going to demo the Inspire, and problem 3, I'm going to demo the 84. And you can do it on the 83 as well. So let's get right to problem 2. I'm going to go ahead and graph this first, and then we'll eliminate the parameter just to make sure you're comfortable. So graph-wise, I'm pulling up my Inspire. I'm at the home screen. And we're going to go to the graphing screen over here. Currently, our entry edit, number 3 down here, is set to a function. However, there are many other entry edits you can change that as, a relation, there are other templates in there, but since we're doing parametric equations, we should probably choose parametric. From here, it's pretty straightforward. X sub 1 of t equals, well, it looks like we're doing the square root of t, aren't we? So the square root of t, and then y sub 1 equals t plus 1. Nothing too bad. Now notice that this t-value is set from 0 to 6.28. And you might think, well, 6.28, that's kind of weird. Why would they pick 6.28? But maybe then you're remembering if you were to take the approximate value of pi is approximately 3.14, isn't it? And then you double it, you get 6.28. So 6.28 is an easy approximation for 2 pi. So why do you think they picked 2 pi? And hopefully you're starting to think, well, wait, 2 pi is one full rotation around a circle. Are we going to be doing circles here? And we certainly are. So you need to be prepared to see shapes that are not just linear or basic curves, basic functions, I guess, but also things that aren't functions like circles or ellipses or anything like that. So let's go back to this and make sure everything looks good. So the square root of t, we had t plus 1, I think. Yep, good. And then I'm going to graph. Now, this is fine, right? It goes from a t value of 0 all the way to a t of 6.28. And here you had to go from -2 to 3. So I'm actually going to change this really quickly. We're going to go back up, hitting tab, and we're going to change our t values. And we want to go from -2 all the way over to +3. What's this t step? Well, that is all the values of t that your calculator is actually plugging in to get a reasonable approximation. Now, if you had a function that did some really weird stuff with small numbers, like maybe at 0.1, it had a value of 10. At 0.11, it had a value of -50. And at 0.12, it had a value of 4 million. Well, you'd probably want to see those individual points to see the graph oscillate, go up, go down. And you might want to decrease your t-step to like 0.01. I want you to plug in all the numbers starting at -2 and going up by 0.01. So -1.99, -1.98. But you might also say, nah, going up by 0.1s is fine. It doesn't really matter. So hitting enter here, you won't see too much else, and you also won't see any negatives over here. Why aren't we seeing any negatives? Well, because this is a square root, and I think when you substitute negatives into a square root, it breaks. So no negatives, and it just looks kind of like a parabola again. That's weird. Let's eliminate that parameter and see what happens. So we have, let's see, x. That's my y equal to t plus 1, and we also, of course, have x equal to the square root of t. I imagine you guys can, it doesn't matter which one you solve. I did x before, so let's work with y. So I'll isolate t over here. So I think that's going to give me x equals the square root of y minus 1. But then we usually like our functions to be in the form, and they'll usually tell you, we want your function please to be in the form of y equals a function of x. Y isolated, things only happening to x. So I think we need to move this around a bit, which probably suggests we square both sides, right? So we end up with x squared equals y minus 1, and then add 1 to both sides to get y equal to x squared plus 1. So this tells us it should be a parabola of x squared plus 1. However, there are some weird restrictions here because we see that technically this cannot be negative. So I think in order to have a complete rendering of this, we would probably have to give a domain, and we would say that the x's, in this case, have to be greater than or equal to 0. Right? Because otherwise it will not match the original parametric equation. You are not required to do this on the AP exam, no stress, but it's never a bad thing to bring in extra math for you. So take a quick second, fill in the rest of your table if you haven't already and the graph. Whenever you're good, if you're on the Inspire, please try the last two and then maybe tune into the fourth problem because there's a little bit of a trick in there. But then if you're on the 84, let's get to the third one. So 84, I'm going to go ahead and eliminate the parameter first just so we can see if we did everything right. And let's see, y equals 1/2 t. I never liked the t over 2. I always write it as 1/2 t. It looks to me like it's a little easier to isolate t, so 2y equals t. And then we work with this guy. So x equals t squared minus 2, way too big, t squared minus 2, and this is 2y. Nice. And then I think we should probably isolate y again. So we add 2 to both sides, like so. This is 4y squared, cleaning up the squared. divide everything by 4 if you'd like, or multiply by 1/4. I actually kind of prefer that. So we can see it's 1/4 times x plus 2 equals y squared. And then last but not least, take the square root of everything. Square root of 1/4 is 1/2, and then this becomes the square root of x plus 2. Did I forget anything? Yes, I think we did. First, equals y, but second, whenever you introduce a square root, you need a plus minus. So to me, a square root with a plus minus with just a plus would look like this. With a minus, looks like this, right? The plus 2 inside is going to shift this 2 to the left. So I'm expecting our graph to look something like this. The 1/2 compresses our graph vertically by just a bit. Let's see if we're right. So 84 time, make sure you have that ready. You're going to want to be on your main screen, your home screen. You don't need to be on the graphing mode at this point. So here's my 84. We'll bump it over here so we can see the problem. And we're on that main screen. We want to go to mode. Currently, there are 4 modes that the Inspire allows you to choose from. We are in function mode. We have parametric, polar, and sequential mode. We talked sequential earlier. Polar we'll do later this unit. We want parametric, please. Now, when we go to y equals, and actually it's probably worth mentioning, running through these 4 right here also runs through the 4 variables that are on this key. X is the input for a function, t is the input for a parametric, theta for a polar, and n for a sequence. So when I go up here and I start pressing this button, no longer do we see x, now we see t. Okay, so I need t squared minus 2, and dropping down one further, our y was 1/2 t, or if you want, t divided by 2. When I graph this, look at that. We only see the positive side, though. That's interesting. I wonder why we only see that positive side. Oh, well, think about the x-coordinate, or I guess rather think about it this way. The values of t that we're plugging in on this calculator probably, just like the Inspire, start at 0. So if you plug in positives here, of course, x will be positive. And if you plug in positives over here, y will be positive. So if they said t is only for positive values, then I think you'd only need the positive right here. Okay? Now, if they said positives and negatives, you need a way to add this extra piece down here, and I'll leave you to figure out how to do that. There is a way to do that on the Inspire or on the 84. It's a little bit trickier, but it is definitely doable. So there's that. Take that knowledge, please. Go ahead and try problem 4. I would like you, before you do any of it, though, to use this table to fill in different values and then try to plot those values over here and see what you come up with. Then you can use your calculator to graph, and we will finish with how to eliminate that parameter. Okay, well, let's take a look at the graph together to make sure you did everything correctly. I'm going to go ahead and do the same thing here, but let's pull this down so I don't mess this up. So we have 3 plus 2 cosine of t. And those of you that are taking physics, make sure you've changed your calculator to radian mode. Calculus is rad. We're not like those weird physics degree peoples. And we end up with this. It's a rather uninspiring graph, isn't it? Kind of looks like a little purple caterpillar here. I'll zoom in slightly, though. Oh, well, we're only going from 0 to 1. What if we went a little bit further, like to 2, 3, 4, 5, 6? There's still a gap. How do we close the gap? Wait, we saw this on the Inspire earlier. What if I go to 6.28? There we go. 0 to 2 pi. So it's pretty fascinating here that when you set your parameters to go from 0 to 2 pi, the circle completes itself. What if you go further? What if you went from like 0 to 10? 15? 16? Nothing is happening, because what's happened at the beginning is the graph starts, at a value of 0, and then just does this part. It's moving up and to the left here. And then it's going to complete this full circle, this full ellipse, I guess, and then it's just going to retrace itself over and over. So it looks like it completes one full egg, one full ellipse, one full elliptical orbit every 2 pi. Huh. Okay, well, let's go ahead then and try to eliminate that parameter and see what happens. Now, full disclosure, eliminating the parameter also does not really show up on the AP Calculus BC exam, but I think it's really silly to just only show you the calculus portion of parametrics and not have a good foundation in parametric equations. Then you're just blindly following steps and not really understanding the connections between parametrics and typical y equals f of x functions and equations. So I do like to spend this extra day. So here we go. Eliminating the parameter. X equals. It's always a fun game to see if I remember how to do this one each year too. So good thing I'm making these videos, and next year I can remember it. I think you'll find that you do not want to isolate t, because if you isolate t here, what's going to happen is you're going to have to introduce, to remove the cosine, you'll have to introduce inverse cosine or inverse sine over here. And inverse cosine and inverse sine have a bit of a defect, a shortcoming, a purposeful shortcoming, but something that makes them very hard to use in mathematics. And that is, we've defined them to be functions, which means they're only going to give you one answer. However, there are technically an infinite number of answers, right? If I ask you for the inverse cosine of square root of 2 over 2, you might say that that's pi over 4, and you'd be correct, because cosine of pi over 4 is root 2 over 2. But someone might say 7 pi over 4, and they'd also be correct. Or you might even say negative pi over 4, and you'd be correct. There's an infinite number of answers, but we've defined it to only give one to keep that as a function. And so if you ever use this math to try and solve an equation outside of basic geometry, you may not get the correct answer, and you certainly won't get all of them. So what can we do here instead of, instead of actually isolating one? Well, here's something you probably didn't think of, and you wouldn't have thought of it, because honestly, I wouldn't have thought of it unless I hadn't looked it up a couple of years ago. I'm just going to isolate each of the individual trig functions. So I'm going to subtract 3 and then multiply by 1/2. So that's going to give me 1/2 x minus 3 is equal to cosine of t. Same thing for y. Add 1, divide by 3, or multiply by 1/3. So 1/3 y plus 1 equals sine of t. It's totally okay to do y plus 1 over 3 as well, whatever is easiest for you. All right, then what? Well, at this point, let's go ahead and square each side of the equation. And this is the weirdest step. You're like, why would I ever think to square both sides? Well, that's a great question, and I wouldn't expect you to. But it is a fun practice in trig functions, so let's see what happens. So we're squaring each side of each component. Well, this side becomes 1/4 x minus 3 squared, and this becomes cosine squared. I'll use that trig notation to put in the 2 inside. And the other one, of course, is 1/9 y plus 1 squared equals sine squared. I see a cosine squared and I see a sine squared. Well, aren't we kind of dealing with a system of equations here? And isn't one way to solve a system of equations by stacking the two equations on top of each other and adding them together? Some people call that solving by addition. Some people call it solving by elimination. And elimination isn't really a great name for this, because we're not actually going to eliminate anything outright here. But what we need to remember about elimination is that we are allowed to add two equations together. Now, in algebra, we only add them when two things cancel out, when they add up to 0. But you can really add any two equations together. And so you might be thinking, well, why would I want to add these together? I mean, if nothing cancels, it just makes a terrible equation. Well, just pretend you trust me for a quick second, and let's see what happens. So we're going to get adding the left side together. 1/4 x minus 3 squared plus 1/9 y plus 1 squared. And then on the right side, we end up with cosine squared of t plus sine squared of t. Well, you're like, well, how does that help? You still have t, but do we? Because isn't there one identity that, even though you don't really have to use it on the AP exam, that pretty much everyone remembers coming out of trig? The Pythagorean identity, which tells us when we have sine squared of a variable plus cosine squared of that same variable, then doesn't that just become 1? And so from here, we end up with 1/4 x minus 3 squared plus 1/9 y plus 1 squared equal to 1. And this is actually a very, very common way to write the form of an ellipse or a circle, or, and there are a couple more, but the hyperbola as well. These are known as conic sections. And you might have wondered, why do conic sections always add up to equal 1? Well, 1 is just convention. It's much easier to have everything equal to 1. But the other is that it turns out many conic sections are written parametrically first because they're a little bit easier. And when you convert it to a function, or maybe not a function, but an equation of x and y, the answer always ends up equaling 1. Pretty wild, huh? And so if we try this on Desmos or your calculator really quickly, let's see if we get the same match. Now, notice here, we are in essentially HK form. Positive 3, and we do the opposite of k as well. I'm looking at positive 3, negative 1. Where is positive 3, negative 1 on my graph? Let's identify that. 3, comma, negative 1. Oh, it is dead center to my ellipse. That is awesome. You'll also notice the ellipse is a little bit taller than it is wide, and that shouldn't be a surprise. We have 1/9 instead of 1/4, so this 1/9 is going to stretch us further up than we are stretched side to side, or you could think compressing more, whatever sounds good to you. So looking at this really quickly, we had 1/4, and then it was x minus 3 squared plus 1/9, and this was y plus 1 squared, all equal to 1. And look at that. We have created the same ellipse that we did parametrically up above. So thanks for tuning in for today. This is a nice either reminder or introduction to parametric equations. You can run to your physics teacher and tell them about how good you are at physics now, and they'll be very proud of you. There are 6 questions we'd like you to try for tonight. With those 6 questions, you're going to be doing the same thing. You're going to make a table of at least 5 values. You can choose the 5, but I'd say maybe 0 through 4 are an easy 5 values. If you're dealing with things where you want nice numbers, you can pick the evens, whatever sounds good to you. Sketch the curve by using your table. Please indicate the direction of your graph by using arrows on there to point the way it's going, right? In this case, with my ellipse, let's see, we had the point 1, 2, 3, negative 1 right here, and then it looked something, this won't be perfect, but it looked something like that. Our direction, though, would have arrows pointing this way to show we're moving counterclockwise because that's how it's drawn. And then eliminate the parameter, if possible. I think they all should be possible, though. And then, last but not least, use your calculator to compare the 2 graphs. So pretty much the same thing we did today, just a few extra problems. As always, I have the solutions of these posted on Teams if you want to check your work against them. But thank you for tuning in. Next class, we'll actually get back to the calculus portion of parametrics. How can we find the slope of parametric equations without putting them all together? It's a pretty exciting process. And keep up the great work. You are almost done with calculus, or at least Calc 2. I am super impressed.